Alright, so today we're going to cover Noether's theorem. This very beautiful theorem, and I'm sure by the end of this video you'll learn to appreciate it. So let's start by considering an isolated system of particles. So you just have a bunch of particles just floating around in space. So n particles, here we'll just have n equals 4. One of the most prominent features of an isolated system is that it is translationally invariant. So that is, if we transport all n particles bodily through the same displacement, nothing physically significant about the system should change. So like, if each position here is able to be described by some r sub alpha, so like this would be r sub 1, r sub 2, etc. And then we were to move it over here by some displacement epsilon, then we move everything the same way. R1 plus epsilon, and then R2 plus epsilon. Basically, one of the prominent features of an isolated system is that nothing physically significant about the system should change. So the potential energy should be unaffected by this displacement. That is to say that U of R1, R2 is equal to U of R1 plus epsilon, R2 plus epsilon, or more briefly, the way that we're going to use this, and we saw this notation in the last video, delta U equals 0, where delta U denotes the change of U under this translation. Clearly, the velocities are unchanged by the translation, because when we take the derivative with respect to time of r, then basically you just get r prime, and then this just vanishes because it's a constant. So the velocity doesn't change. Therefore, the change in, I'll write it up here, therefore the change in kinetic energy is also going to be 0. So the Lagrangian is defined as the kinetic energy minus the potential energy, right? And so if the kinetic energy and the potential energy don't change, then the Lagrangian doesn't change for this displacement. So this is an example of a mathematical symmetry, which is a type of invariance. It's a property that a mathematical object remains unchanged under a set of operations or transformations. So here what we're saying is, under a set of spatial translations, an isolated system will have its Lagrangian invariant. A continuous symmetry is the intuitive idea of viewing some symmetries as continuous motions. So for example, epsilon is a continuous variable as opposed to a discrete variable. And we talk about continuous symmetries as opposed to discrete symmetries, such as, for example, reflection symmetry, which is invariance under some sort of a flip. And so Noether's theorem is that if a system has a continuous symmetry property, then there are corresponding quantities whose values are conserved in time. So in our context, for each symmetry of the Lagrangian, there is a conserved quantity. The symmetry that we have just observed right here is called spatial translation invariance. And it serves as an example of Noether's theorem. If we choose epsilon to be some infinitesimal displacement in the x direction, then all the x coordinates of the particles increase by epsilon. The y and z coordinates are unchanged. So the change in L is equal to epsilon. Here, I'll write it like that, keep it consistent. Epsilon times dl over dx1 plus epsilon dl over dx2 plus and so on. And then we have that equal to 0. So basically for a system of n particles, we have just the sum of these, the index is equal to the index being alpha, and the Lagrangian with respect to x alpha equals 0. Now, using Lagrange's equations, we can rewrite each derivative as dl over dx sub alpha equals d over dt times dl over dx prime alpha. And these are just Lagrange's equations. And that's just going to be equal to d over dt of the momentum of this alpha particle in the x direction. Thus, this right here becomes, and I'm going to run out of space, so let's erase this. This right here becomes the sum of the time derivative of momentum for each particle is equal to 0. So this means that the total generalized momentum is equal to 0, and that by choosing the small displacement epsilon successively in the y and z directions, we can prove the same result for the y and z components. So we reached a conclusion that the spatial invariance of the Lagrangian implies conserved total generalized momentum. So note that if the partial derivative of u of x with respect to x is not equal to 0, which means that the potential field will change, then the potential energy is not stationary for small displacements. So that is delta u is not equal to 0, which implies that delta L is not equal to 0, and the symmetry is broken. So recall that Newton's law states that force equals minus delta u over delta x, du over dx. So by saying that delta u is not equal to 0, it implies that there is a force that is acting on the system, at which point it is no longer an isolated system. So conclusively, the translational symmetry is broken if the system is in a non-trivial potential, non-trivial meaning not vanishing with differentiation. Momentum is not conserved either because, again, by Newton's second law, force generates a change in momentum. Consider a time-dependent Lagrangian. By the chain rule, the time derivative of the Lagrangian is going to be equal to the sum of the partial derivatives with respect to qi times time derivative of qi, summing over the generalized coordinates, plus the sum of partial of L over partial q prime I times q double prime I, which is just acceleration, plus dl over dt, partial L over partial t. By Lagrange's equation, for the first sum, this part right here is just d over dt of delta L over delta q prime I, which is equal to d over dt of momentum, which we'll just represent as momentum prime. Meanwhile, for the second sum right here, this is just generalized momentum, so that's just pi. So we can rewrite the time derivative of the Lagrangian as the sum of the product of p prime I, I wrote that too close, q prime I plus pi q double prime I plus the partial of the Lagrangian with respect to time, which is just going to be equal to the time derivative by the chain rule of the sum of momentum times velocity over these generalized coordinates plus partial L over partial t. For many interesting systems, the Lagrangian does not depend explicitly on time. So for many interesting systems, we'll have this is equal to 0. When this is the case, the second term on the right is this term right here is going to vanish. And if we move the left side to the right, we can see that the time derivative of the sum of delta, the sum of pi q prime I minus L is equal to 0. And in fact, this quantity is so important that we give a name to it. We'll move it right up here. This is quite an important quantity in physics, and you'll see it a lot in higher physics and quantum mechanics. It's called the Hamiltonian. And it's defined as that quantity. So provided that the relation between generalized coordinates and Cartesian coordinates is time independent, then we have that the Hamiltonian is equal to kinetic energy plus potential energy, which is just the total energy. So the following theorem is that if the Lagrangian does not depend explicitly on time, then the Hamiltonian is conserved. To prove that the Hamiltonian is total energy for natural generalized coordinates, let's express the total kinetic energy as T equals 1/2 of the sum of masses times radii prime squared in terms of the generalized coordinates. By the chain rule, this right here, this r prime, is just going to be the sum of the derivative of this r prime, of this r alpha with respect to qi times q prime of I, summing overall of the generalized coordinates. The scalar product of this equation, this with itself, will be r prime squared is equal to the sum with the index of j of the derivative of r sub a with respect to q sub j times q prime sub j, and that quantity times the sum with k as its index of ra over qk q prime k. Therefore, we can basically say that this kinetic energy is just 1/2 of the sums over j and k of some a jk q prime I times q prime j, where we have defined a equals a, I should add sub jk equals the sum over the alphas of m alpha dr alpha dqj times dr alpha over dqk. Differentiating the kinetic energy with respect to q prime I yields the generalized momentum. So we have p sub I equals partial L over partial q prime of I, equals partial T over partial q prime of I, which is just equal to the sum over the j's of a ij q prime j. So what we can rewrite for the sum from the definition of the Hamiltonian is that pi q prime I is equal, which is just equal to 2 times kinetic energy if we compare it to our result right here. Therefore, the Hamiltonian is equal to, which is equal to this sum right here, pi q prime I minus Lagrangian, is equal to 2t, because this is 2t, minus t minus u, which is Lagrangian, which is equal to t plus u. It is thus another example from Noether's theorem that a system for which the Lagrangian is invariant under time translation has its total energy conserved.